Hello everyone, my name is Reza Pirayesh. Today I'm going to briefly discuss one part of my PhD research, which is focused on a space mission called Virtual Telescope for X-ray Observation. This part of research is funded by the New Mexico NAVSA score, and we use the resources of Argonne Leadership Computing Facility for the data, the machine learning, simulation, optimization. So the name of the title of this paper is Intelligent Real-Time Robust Nonlinear Attitude Control for Virtual Telescope for X-ray Observation. These are the previous published work on this research by me, and this is the mission. So it's the Virtual Telescope for X-ray Observation, the name of the mission, and the attitude formation control should maintain a 55 milliarcsecond accuracy in the science observation, where the observation of the space objects take place. The orbits are highly elliptical supersynchronous geostationary transfer orbits, and the distance between the imager satellite and optic satellite are 1 kilometer. So the application of this telescope is applications are investigating the nature of space, understanding more about black holes. We can cover the sun. We can detect space phenomena like the detection of stars collision. We can find extraterrestrial life. And in the optic satellite, we use the Fresnel lens. And you can see the image of a Fresnel lens. It is discussed more in this paper. The objects we want to observe are given in this list. And these are the collection, the time that the science observation with 55 milliarcsecond have takes place. For example, you can see for the crab pulsar, we want 16 hours. So uh, in the apogee, 16 hours of observation should take place. So we have 6 novelties in the paper. And in this presentation, we discuss more of the core of the research, which is the first novelty, and the rest of them are discussed more in details in the paper. So the novelties of the paper are we define an asymptotic machine learning based optimal Lyapunov attitude controller based on the virtual telescope for X-ray observation, mission phases, instrumentation, and requirements. So I will discuss more the requirements, instrumentation, and phases briefly. So we introduce a robust Ranch-Kutta solver for solving the quaternion equations. We integrate the adaptive Ranch-Kutta solver in the data production and optimization process for a time-efficient data production to reduce the computation time while maintaining high accuracy for the attitude control system solver. We find the optimal nonlinear Lyapunov attitude controller parameters for attitude control system by Monte Carlo Simulation. We integrate the weights of the learning machines with the desired distribution to provide an accurate, diverse, and spread Pareto set for the posterior to find a single solution in the machine learning. The machine learning hyperparameter optimization is performed with a systematic approach to the computation resources for VTXO. So in this part, the hyperparameter optimization is specifically performed on the supercomputers in the Argonne National Laboratory. So the mission phases and instrumentation, we have 3 phases for the attitude control system and 4 for the position formation. The first phase for the attitude control system is the formation stabilization phase, and then we have the transient phase, and next we have the science observation phase. So the plan for each one of them, the time and everything depends on the mission, and also the phases of position formation are the deformation phase, the tracking phase, the formation phase, and the science observation phase. So the science observation is happens in both of them, where we observe the objects that are specified for the VTXO, and each one of these phases are planned based on the instrumentation optimization discussed in other papers and this paper as well. So the instrumentation or the we have the star tracker, we have X-ray camera, GPS, avionics, thrusters, laser, navigation beacons. We have the band radio for ground and inter-satellite communication and radio ranging. We have the propulsion system. We have the optics. So we are going to focus more on the transient phase, and these are the transient phase requirements. So these requirements, as you can see, are based on they are defined based on the because of the star tracker and because of the field of view of the telescope. So the first requirement is the final slew error of optic satellite is less than 5 degree. The final slew error of optic satellite plus the final slew error of the imaging satellite is less than 5 degree, and the spacecraft, each one of them should have a slew rate error near zero to start the observation phase. So this, as discussed, it was the phase before the observation phase. And then the accuracy requirements because of the field of view our final slew error of the optic satellite should stay less than 0.15 degree. For the imaging satellite, the final slew error should stay less than 0.118 degree. And then the final slew error of optic satellite plus the final slew error of the imaging satellite should stay less than 0.18. So this is the framework of the artificial intelligence that we use so that we can satisfy these requirements. So here there is the data production phase where we use the simulated annealing optimization algorithm here. This is the final trajectory uh, which are obtained based on these objects, as you can see in the sources. And this is the weight. This is the optimization. And in the machine learning phase, we use support vector machines, Gaussian process, and deep neural network to train the machine learning for the data. And we show that the deep neural network is chosen because it provides the best performance, which can satisfy this mission requirement. In the implementation phase, the estimated initial condition from the sensors and attitude estimation algorithms are read are given to the machine learning, and also the weight and the desired final trajectory. And then we obtain the estimated output of the machine learning. This estimated output of the machine learning is shown to satisfy the energy error, the error requirement, the energy it provides 0.47 joule, which is good for the mission, and it provides us with this machine learning provides us with the optimal controller parameters, which can minimize the error and energy given here in the objective function. So in the paper, we discuss the hyperparameter optimization and the rest of the novelties, and I hope this was helpful with this was this presentation was helpful with the paper. Thank you for listening.